Suppose I were going on a trip to Japan and I wanted to know how much my US dollars were going to buy in Japan. What I want to do is look up how many yen I get. The yen is the Japanese unit of currency. So I'd look up maybe on the internet how many yen I get for each US dollar. And then using that as a conversion factor, I'd figure out how many yen I could get for my US dollar. So suppose that I look it up and it turns out that 1 US dollar, abbreviated USD, is equal to 106.823 Japanese yen. That's a relationship between dollars and yen. And the beauty is that you can take those sorts of relationships and turn them into factors of one, or unity factors, or whatever you want to call it. The point is that they are going to be dimensionless numbers overall, so you can multiply anything by 1, and you can use that to do your conversions. So if we take this relationship and we divide through by 106.823 yen, so divide both sides by that number, then we would get a relationship, so ignore my hands for a moment, and we would get a relationship that looks like what's left over here. In other words, $1 divided by 106.823 yen is equal to 1. Okay? And then if we did it the other way around, if we divided both sides of this equation by $1 instead, we would end up with an equation that looks like that 106.823 yen divided by $1 is equal to 1. What are we doing? Well, we're taking the units along for the ride, and that's the key. We always want to take the units along for the ride. And if we take the units along for the ride, what we get are a bunch of things that actually amount to 1, and we can multiply by one of these factors or one of these factors without penalty. In other words, we can do it and we affect a conversion, but we haven't changed the value of the number. All right, so let me express this by doing a conversion. Suppose I have 50 bucks. I want to know how many yen that's going to amount to. You take, what we're trying to find out is the number of yen in $50. So let's put that over on the left. And the answer has to be in yen. So overall, the units have to end up being yen. We take $50, which is the number we're trying to convert, i.e. it's the data, and we include the units. And then we take a conversion factor, and the conversion factor could be either this guy or this guy, and we have to decide which of these are we going to use. We can multiply by either one with impunity because, again, they amount to a factor of 1 when you include the units along for the ride. Well, which one of these are we going to choose? And the answer is we want to choose the one which allows us to cancel out the units that we don't want. So we don't want dollars. So that means we want to choose the conversion factor that has dollars in the denominator, and then we'll have yen in the numerator, because the dollars are going to cancel out, and we can actually go ahead and cancel out the units. So we'll cancel out dollars with dollars, and then we multiply 50.00 times 106.823, and then we have 4 significant figures here in our original number, so the overall conversion is the number of yen in $50.00 is 5,341 yen. That's all there is to conversion factors, with the exception that you might have to use more than one conversion factor, and I'll ultimately show you that. Now, there are all kinds of different conversion factors. There are all these that you're familiar with. 1 foot is equal to 12 inches, 1 pound is equal to 16 ounces, blah, blah, blah. And one thing to understand is that these are considered exact. And being exact, what's implied is that there are infinitely many significant figures. So 1.00000000000 feet is equal to 12.000000000 inches. In other words, these sorts of conversion factors and any other that you might write or that you are given do not limit the number of significant figures. It's the data that limit the number of significant figures. And so going back briefly, it wasn't that $1 limited our significant figures, because this is a conversion factor, so these numbers are considered exact. It's this number here, the data, that limited our number of significant figures, and we wanted to limit it to 4 because there are 4 here, and so there's our answer. Now, there is something else that can be exact, and that is things that are counted. In other words, a family has 2 children, that's considered to be an exact number, 2.0000000. So if you wanted to ask how many ears are in the family, how many ears are on the children, it would be 2 per children times 2 children exactly. So you don't worry about limiting significant figures with counting things. All right, so suppose we wanted to calculate the flow rate of Niagara Falls, and we know in gallons that it's 1.5 times 10 to the 5th gallons per second, and we want it in liters per second, so it's a nice metric unit. And we have the identity that 1 gallon is equal to 3.7854 liters. So we can remember, make two different factors of 1 from this relationship. And the one that we're going to want is the one that allows us to cancel out gallons. Okay? Because gallons is in our data, and we want to cancel out the gallons, and what we want is we want liters left over, because the answer has to be in liters per second, which is the rate. And think about this, though, that seconds, which is in the answer, and seconds, which is in the data that we're starting with, that's going to go for the along for the ride, and nothing's going to happen to it. In other words, we're sort of halfway there already. We have seconds in the denominator of our units in both the answer and the piece of data that we're starting with, so that's okay. All we have to do is correct for the gallons. So we'll use a unit of 1, which has gallons in the denominator so that we can cancel out the gallons. And then we'll use this liters, 3.7854 liters in the numerator. And again, gallons cancel out. And then we multiply 1.5 times 10 to the 5th times 3.7854 liters. And then two significant figures here, because 1.5 has two significant figures. And so the rate of water going over Niagara Falls in metric units is 5.7 times 10 to the 5th liters per second. Now, I was mentioning that seconds is going along for the ride here, but what happens if we're trying to convert both the numerator of our unit and the denominator of our unit? For instance, a car is traveling 75 miles per hour. What is its velocity in meters per second? So we have to convert miles into meters, and we have to convert hours into seconds. And for this problem, we're going to need a whole bunch of different conversion factors. We have that 1 mile is equal to 5,280 feet and blah, blah, blah. And you can read all of these, and they're probably mostly familiar to you. The one that might not be familiar is 1 inch is equal to 2.54 centimeters, and that's the unit that relates length in the British unit to length in the metric system. And this is actually, again, an identity. It means that 1 inch is exactly 2.54 centimeters. Okay, so we want a rate, and we want it to end up to be in meters per second. And we start with our data, which is 75 miles per hour. And then somehow we have to get rid of miles and turn it all into meters. Well, we have a conversion factor involving miles and feet, and we want to use it with miles in the denominator and feet in the numerator. So there's 1 unit of 1. And then we have to get rid of the feet because we want to get it into meters. So that's 12 inches over 1 foot. That's another unit of 1. And then now we have inches, but we wanted to get into centimeters. So we'll use our 2.54 centimeters over 1 inch. And now we have to get it into meters, and so we've got centimeters in the numerator, so we put centimeters in the denominator and put a meter in the numerator, and there are 100 centimeters in 1 meter, so that's another unit of 1. And now we have to deal with the seconds, with the hours. We want to get rid of hours. Hours in the denominator here, so we'll put hours in the numerator and minutes in the denominator. And then we don't want minutes, we want seconds, so we have to put minutes in the numerator, seconds in the denominator. And the key is that all these units are going to cancel out. So miles cancels out with miles, feet cancels out with feet, inches cancels out with inches, centimeters cancels out with centimeters, hours cancels out with hours, right? Denominator, numerator. Minutes cancels out with minutes. What's left over? Well, all these things are canceled out. We have meters here and seconds, and that's exactly what we want. So you multiply 75 times 5,280 times 12 times 2.54, divided by 100, divided by 60, and divided by 60 again, and we get 34, and we reported to two significant figures because we started at 75 miles per hour. So 75 miles per hour corresponds to 34 meters per second. Now, the final conversion sequence that I want to tell you about is converting from degrees Celsius to degrees Fahrenheit. And very often in textbooks, you'll see expressions that look like the blue conversion sequences here, where whatever the temperature is in degrees Fahrenheit, you subtract 32, multiply by 5/9, and that gives you the temperature in degrees Celsius. Alternatively, if you take the temperature in degrees Celsius, multiply by 9/5 and add 32, you get the temperature in degree Fahrenheit. And the key is these two expressions just tell you that 32 degrees Fahrenheit, which is where water freezes, is equal to 0 degrees Celsius, and 100 degrees Celsius, which is where water boils, is equal to 212 degrees Fahrenheit. Well, what's wrong with these expressions? And the answer is they aren't good about keeping track of units. The units are implied, but I'm in a second going to show you exactly what they should read. Again, the key is bring the units along for a ride. Trust me, I do this myself. When I'm doing these sorts of conversion factors in my laboratory, I keep the units. I drag the units along and make sure they all cancel out and make sure everything works out right. That's how you don't make a mistake. So what should these temperature conversion equations say? They should say the temperature in degrees Fahrenheit minus 32 degrees Fahrenheit, so this whole expression is in degrees Fahrenheit, and then multiply by a conversion factor 5 degrees Celsius for every 9 degrees Fahrenheit, and then the units are going to work out to give temperature in degrees Celsius. Okay? And similarly, there's an expression that relates temperature in degrees Celsius to temperature in degrees Fahrenheit, where now the units all work out. So, these things are actually going to be true to their units. Now, the final one I'm going to mention here is that we're going to ultimately learn something called the Kelvin scale, and the Kelvin scale is related to the Celsius scale. The size of the degree is exactly the same, so 1 Kelvin divided by 1 degree Celsius. And then there's an additive constant, 273.15 kelvins, and that's how we get from the Celsius scale to the Kelvin scale. If you're not familiar with it yet, don't worry about it. It's going to come up later. So remember, always include the units. When you're asked to work a problem, figure out what the units are supposed to be in the answer, figure out what units you've got to start with, what your data look like, and then arrange a series of unit factors, units of 1, that allow you to get all of the units to cancel out to give you the units that you want in your answer, and you'll be safe and you'll get these problems correct.